Okay, 6.4 rates of change in quadratic relations. So first differences. These are the differences between the y values that correspond to consecutive x values. Okay, the rate of change of y values with respect to x values. Okay, a linear relation has constant first differences, and we learned that in grade 9. And a quadratic relation has constant second differences. Okay, example 1. Complete the table of values, first and second differences for this equation here. Okay, so we have y equals x squared plus 5x plus 4. For the x values from -5 to 0. So what we're going to do is we're going to put all these numbers in the x values. Okay, -5, -4, -3, -2, -1, and 0. And then what we're going to do in the y column is we're going to actually sub this in. So it'd be like -5 squared plus 5 times -5 plus 4. And we're going to solve for these. Okay, so -4 squared plus 5 times -4 plus 4. Okay, and I'm going to do one more, but then I'm not going to show my work for the other ones. -3 squared plus 5 times -3 plus 4. And we're going to go all the way down and do the same thing. So we get 4, 0, get -2, -2, 0, 4. Okay, in regards to first differences, we're going to go up the y column and we're going to subtract. So we're going to go 4 minus 0, and that's 4. 0 minus -2, and that's 2. -2 minus -2, and that is 0. We get -2 minus 0, which is -2, and then 0 minus 4, which is -4. Now we're going to do the second differences. We're going to go up the y column, and we're going to subtract the first difference values. So 4 minus 2, I get 2. 2 minus 0, I get 2. 0 minus -2, that turns to positive 2. And then -2 minus -4, it turns to positive 2. Okay, we can determine by the second differences being constant that this is quadratic. Okay, therefore quadratic. And we're going to go ahead and we are going to graph these points. Okay, so I'll start with these ones, 0, 4, -1, 0, -2, -2, -3, -2. That means the vertex is going to be somewhere in here. I'll make this a little darker. Okay, vertex is going to be somewhere here. And then this is symmetric. So we have this, and then we have this. Here we go. Okay, and we want to go y equals x squared plus 5x plus 4. Okay, example 2, determine if each of like the following table of values is linear, quadratic, or neither, right? So as soon as we see table of values, we're thinking, okay, I'm going to find the first and second differences. Okay, first differences, so we're going to go up this y column here. 15 minus 11, I get 4. 11 minus 7, I get 4. Okay, I'm not going to write these out anymore. 7 minus 3, I get 4. 3 minus -1, I wrote this out because it's a double negative. Again, 4, and then we get 4. As soon as we see that the first differences are constant, we know it's linear. You do not have to do second differences. The second differences will all go to 0. That doesn't really tell us anything, okay? Okay, next one, 64 minus 32, I get 32. 32 minus 16, I get 16. 16 minus 8, 8 minus 4, 4 minus 2. Okay, the first differences here are not constant, so we're going to go ahead and subtract these up the first difference column and find the second differences. 32 minus 16 is 16, 16 minus 8, 8 minus 4, and 4 minus 2. Okay, second differences are also not constant, therefore this is neither linear nor quadratic. Okay, and now the last one, 9 minus 4, I get 5, 4 minus 1, I get 3, 1 minus 0, 0 minus 1, 1 minus 4. Okay, second difference is going to do the same thing. 5 minus 3 is 2, 3 minus 1 is 2, 1 minus, and remember this is the double negative, 1 minus negative 1 is 2, and negative 1 minus negative 3, again 2. The second differences are constant, therefore this is quadratic. Okay, example 3. A tennis stadium is designed for optimum viewing of tennis matches. The cross-section of tennis matches, repeat here, that's okay, of a tennis stadium is a parabolic curve. This means that it's a parabola, therefore it probably looks like this, okay? The lower level seats rise in a shallow curve from the floor. The upper level seats are steeper. This ensures that everyone can see the court properly. Petra takes a photograph of the interior of the stadium and superimposes it on a grid. That means whether the stadium is a parabola opening down or a parabola opening up. What she did is she said, okay, let's call this X, let's call this Y. She just drew it with a grid on it. Okay, so what we're going to do is, she makes a table of values. So this is the table of values that she gets from her grid that she puts on top of her picture. We're going to calculate the first and second differences. And then, does this table of values depict a linear, quadratic, or neither? Okay, so height. What is 3 minus 1.8? I get 1.2. 1.8 minus 1, I get 0.8. 1 minus a half, I get a half. Half minus 0, I also get a half. 0 minus 5, I get negative a half. 0.5 minus 1, I get negative a half. 1 minus 1.8, I get negative 0.8. And then going up here, I get negative 1.2. Okay, so we know that it is not linear. Okay, the first differences are not constant. Okay, second differences. Let's go up this column and subtract. 1.2 minus 0.8, I get 0.4. 0.8 minus 0.5, I get 0.3. 0.5 minus 0.5, I get 0. 0.5 minus negative 0.5, I get 1. Negative 0.5 minus negative 0.5, again I get 0. Negative 0.5 minus negative 0.8, I get 0.3. And negative 0.8 minus negative 1.2, I get 0.4. Okay? So, it is not quadratic either. It is neither. Okay? Therefore, neither linear or quadratic. Okay, please note x values must be changing by a constant amount before you can analyze the change in the y values. So all that means is that, like, if you take a look at these x values, they're going up by 2's. Negative 8, negative 6, negative 4, negative 2, and then obviously 0, 2, 4, 6, 8. Okay, so even though to them the stadium initially looked like a parabolic curve, it is actually neither when she took a picture and graphed it.